Hello, Calculus 2. I want to say more about parametric equations. So far I've been giving you some and we've been thinking about them. You know, the opposite question is when we say you have to find the set of parametric equations. So this, I made up one here. Find a set of parametric equations for the line, I guess it goes through these points, -2, 1, and 4, 5. So I didn't even draw the line, but there's a couple of points. So, you know, I can find the rectangular equation for that line real easy. That's algebra, right? First you should find the slope. Let's see, subtract your y's. 5 minus 1 over 4 minus -2. That's the point 4, 5. That's the point -2, 1. I think I did that right. Subtract your y's, subtract your x's. That's the slope, 4 over 6, or 2/3 is the slope. I like to use the point slope form, so then I'll go y minus 5 equals 2/3 times x minus 4. That's how I tend to do it. So there's the equation of the line. I like to distribute and clean it up. Let me see here. That's 2/3 x minus 8/3. If I add this 5, I'm adding 15/3. So I think I get y equals 2/3 x plus 7/3, I guess. Added 15/3, yeah, I guess that's it. So now, but how do I get a set of parametric equations for this? And the truth is, if there's no real restrictions or anything weird, it's easy, super easy. All you have to do is let x be t. And if x is t, what's y? I guess y is 2/3 t plus 7/3. And you found a set of parametric equations for a little particle traveling on this line, if you wanted to think of it like that. You didn't do anything too interesting. I mean, what we got is if x is just t, then as t increases, x increases. So we are just on this infinite, we are on this infinite line, and we're just traveling this way. I guess if they wanted me to travel the other way, now I could adjust that. I could make it a -t. I think that would make it travel the other way. So put a -t there, a -t there. You know, what if they wanted me to travel faster on the line? I could have made the x a 3t. If I would have made the x a 3t, I plugged the 3t in there. The 3's cancel, and it changes here. But if x is a 3t, I plug a 3t in for x. The 3's cancel. I get this equation. That's a different set of parametric equation. It still travels on that line, and it still travels that way. It's just it is going faster. It's for each unit of t, I'm covering more distance on this line. So parametric equations are interesting. Both this one and the one I had a second ago, they would both result in a rectangular equation that's this. So this is the path, but the way they travel on that path is different. You know, what if I wanted it to oscillate back and forth on that path? We've talked about that. Maybe I should let x be, maybe x should be a cosine t. Or how about a 3 cosine t? If x is a 3 cosine t, then I can plug it in here, and the 3's cancel, and I get 2 cosine t plus 7/3. So now I'm traveling on this line, and I bet I'm oscillating. And in fact, I'm not traveling. Now I'm not traveling on the whole line, if you remember from previous videos. Now x is restricted. It only travels between -3 and 3. Now x only travels between -3 and 3. So it actually doesn't even reach that point 4, 5. I should erase a big chunk of this line. It's traveling on that line that contained the 4, 5, but now it's oscillating back and forth on this line. Because cosine spits out answers between -1 and 1, x is now stuck between -3 and 3. So it depends on the question. It depends what's going on. I took one little easy question and I kind of elaborated it quite a bit here. Let's do another one. What if I want to find a set of parametric equations for a circle? And we'll say the circle is oriented clockwise. And we'll also say it's got a radius of 4. We're also going to say it's centered at the origin. And we're going to say one more thing. As it travels around this circle, it does one revolution for t from 0 to 4 pi. So, this is a cool question. I like this question. The previous video, we talked about circular motion. It's not too difficult. I'm going to set up parametric equations for x and y. It's pretty easy. It's a set of parametric equations. If I've got a circle of radius 4, I put a 4 here. And then I put a cosine and a sine, except I remember from the previous video, if x is cosine and y is sine, that's sort of the typical counterclockwise rotation. And they wanted clockwise. Yes, they wanted clockwise here. So that's clockwise is when you can remember it a couple different ways. I've remembered it to where x is a sine. So when x is sine, that's going to be oriented clockwise. So y will be cosine. So that's it. And then I put a t in here. But if I put a t in here, that means it does one revolution. The period would be 2 pi, and it does one revolution in 2 pi. They want me to do one revolution in 4 pi. So they've stretched out the period. So what I've got to do is I've got to find this coefficient in front of t. So, you know, it's for temporarily, I'll call it omega. We often refer to it as omega t. And so, hang on, so what do I usually do? I got to work this backwards here a second. To find the period, I would take 2 pi and divide by that number. So 2 pi divided by omega would be my period. They just told me the period. They want one revolution is the definition of what a period is. So one revolution, they want the period to be 4 pi. So they want the period to be 4 pi. So I do a little algebra to find omega. Multiply by omega, divide by 4 pi. And I think omega is 2 pi divided by 4 pi. The pi's cancel. I guess that's 1/2. Omega is 1/2. So if you don't mind, I'll just do this. 1/2 t, 1/2 t. Yeah, that makes sense, I think. You know, when I had a 2t or a 3t, that shortened the period, sped up the motion. What I've done here is I've elongated the period, and so my coefficient is a 1/2. I've elongated the period, slowed down the motion a little bit here. Yeah, that's it. I did what they asked. It really wasn't that hard. Students, I notice, have a hard time with this part, getting this omega, getting this coefficient correct here. But I think that explains it pretty well. All right, good luck.